Welcome, fellow travelers. As we journey through the vast unknown, we find ourselves exploring the very heart of the universe, a place where motion is constant, yet we often feel still. We are caught in an intricate dance, our lives marked by cycles that have no clear beginning and no end, a cosmic rhythm that carries everything along, even if we don't always notice. But what if everything around us is trying to tell us something profound, something that goes beyond physics and touches on the essence of life itself? Let's begin our story in a place where motion and stillness collide, right here on our very own planet Earth. A planet that spins at over 1,000 miles per hour, orbiting the Sun at nearly 67,000 miles per hour. Yet, despite all this, we feel no movement. Our hearts beat, our minds wander, but the universe spins around us without any noticeable effect. Is this the greatest illusion of all, or is there something deeper at play? An underlying truth we've yet to understand. Every moment we live, we are part of something much larger than ourselves. The Earth, like all celestial bodies, is spinning, not just in place, but in the very fabric of space itself. The laws of motion that govern everything, from atoms to galaxies, seem constant, smooth, and quiet. But as we peer deeper into the night sky, we begin to realize that what appears as stillness might be a powerful illusion, a deeper, more profound force at work. As you breathe, Earth spins. As you walk, the universe dances around you, quietly shaping your world. From the smallest quarks to the largest galaxies, motion is the thread that weaves everything together. Yet despite this constant whirl, we feel no disturbance. Why? The answer is rooted in inertia, one of the most fundamental laws of physics, described first by Sir Isaac Newton. Simply put, an object in motion will remain in motion unless acted upon by an external force. And because we move with the Earth together in perfect unison, we don't feel the ground shifting beneath us. This is why the coffee in your cup doesn't ripple, why the stars above seem frozen in time. This paradox of motion and stillness is not just a quirk of Earth, but a universal phenomenon. From electrons spinning within atoms to entire galaxies revolving through space, rotation defines the cosmos. Yet, on the grand scale of things, why do we experience it as stillness? To answer that, we need to explore not just the physical, but the philosophical, the very nature of how we perceive the world around us. Let's zoom out for a moment and consider the astronauts who float weightlessly in space. They orbit Earth at speeds of 17,500 miles per hour, yet inside their spacecraft, everything is calm. No jolt, no trembling. The motion of the spacecraft feels completely still because, much like Earth's spin, there is no resistance, no change to alert the senses. It's as if time itself has been suspended and we are simply floating along in this cosmic river, carried by the momentum of our celestial motion. This seamless experience of motion is called uniform motion, and it's the reason why you don't feel the speed of the plane you're traveling in, even though it's moving at 500 miles per hour. It's only when the smooth flow is interrupted by turbulence, by a shift in the steady rhythm, that we feel the force of movement. The same principle applies to Earth. Its motion is so steady, so unbroken, that it is as if we are gliding through space unnoticed. Yet this smooth motion shapes everything around us, from the rising and setting of the sun to the very seasons we experience. But there's more to this story. Our Earth's rotation is not just a convenient, unnoticed rhythm. It's a vital force that affects the very structure of life itself. The Earth's 24-hour cycle gives us day and night, but it does so much more than that. It stabilizes our climate, drives weather systems, and helps protect us from the harmful rays of the sun. If Earth's rotation were to slow or stop, half the planet would be bathed in unrelenting daylight, while the other half would be plunged into eternal darkness. Life, as we know it, could not survive. And yet, as we look even deeper, we realize that the Earth is not just spinning in isolation, it's part of a larger cosmic dance. The entire solar system is in motion, traveling through the Milky Way at speeds near 500,000 miles per hour. Every star, every planet, and every particle within it is spinning, yet we remain unaware of it. We are part of this great movement, and yet we experience none of it. How is this possible? The answer lies in the relationship between motion and time itself. As we travel through space, the spinning of the Earth defines the cycle of time. Our days are determined by the planet's rotation, and our years by its orbit around the Sun. But if we look beyond Earth, we see that this motion is not unique to us. The Sun itself spins, as do all the stars in the universe. Even galaxies rotate, spinning through the vastness of space like cosmic whirlpools, each one carrying billions of stars in a grand spinning ballet. Time, it seems, is inextricably linked to this motion. Every rotation, every orbit, every pulse of the cosmos echoes through the fabric of space, shaping the very flow of time. From the smallest particle to the largest galaxy, the universe is alive with motion, and through this motion, time moves forward. Yet, because we are immersed in this flow, we cannot perceive it. We are part of it, locked in a silent, eternal rhythm that stretches from the beginning of the universe to its ultimate end. Now, as we journey deeper into this mystery, we begin to see that the very nature of time and of the universe itself is not static, but fluid. Every moment, every particle, every movement is part of an ongoing story. A story that began long before Earth, long before the stars, and perhaps even long before the universe itself. So let's pause for a moment and reflect on the first question that started it all. Why does everything in the universe move, yet we feel so still? The answer may be more profound than we realize. We are not separate from the motion of the universe. We are part of it. And as we continue our journey, we will explore not just the motion of planets and stars, but the very fabric of reality itself, the forces that shape the universe, that bend space and time, and that ultimately define the rhythm of existence. Take a deep breath and feel the motion within you. You are spinning, always have been. And the stillness you experience is the harmony of everything moving together. We are not just in motion. We are part of the motion. And as we delve deeper into the mysteries of the cosmos, we will discover that this motion is not just a phenomenon of physics, but the very heartbeat of existence itself. As we continue our journey through the cosmos, one question lingers in the air. Who set the universe spinning? This isn't just a question about motion, it's a question about the very origin of everything that we know, everything that has ever been, and everything that will ever be. If the universe is in motion, spinning, twisting, and turning, then who or what set it into this endless, beautiful whirl? To answer that, we must travel far back in time, far beyond the stars, beyond galaxies, and even beyond atoms. We must travel to the moment when the universe was born, when all that we know began as a singular, unimaginable event, the Big Bang, the birth of everything. A moment when everything that exists today, from the smallest quarks to the largest superclusters of galaxies, was once compressed into an infinitely small point, a point of unimaginable heat and density, the very beginning of time itself. But what happened in the moments following the Big Bang? What was the first force to emerge? What was the origin of this motion that would ripple through the fabric of space and time, creating the universe as we know it? The first seconds after the Big Bang are still a mystery to us. They lie in the realm of quantum physics, where the laws of nature become strange and unpredictable. Scientists call this time the Planck era, a brief period just after the Big Bang when the universe was so hot and dense that the forces of gravity, electromagnetism, and the strong and weak nuclear forces were all unified. At this stage, our current understanding of physics breaks down. The equations of general relativity and quantum mechanics don't match up. But what we do know is that even in those earliest moments, something extraordinary occurred. As the universe expanded and cooled, tiny quantum fluctuations began to occur. These fluctuations were not random. They were the echoes of something more profound. Some scientists suggest that these fluctuations could have been the first signs of rotation, a subtle motion that began with the very birth of the universe. a motion that would shape the universe's evolution from the formation of the first atoms to the creation of stars, planets, and galaxies. But what does this mean for the question of who set the universe spinning? It means that the universe may have been born with motion already encoded in its very DNA, not an external force giving it a push, but an inherent property of the universe itself, a subtle primordial rotation that became the foundation of everything that followed. But there's more to this story, because scientists have discovered something even more intriguing. In the cosmic microwave background, the faint afterglow of the Big Bang, astronomers have detected tiny irregularities in temperature. These variations are so small, only a few millionths of a degree, but they hold a profound secret. They suggest that the early universe wasn't perfectly uniform. There were slight differences in density, tiny ripples in the fabric of space that would later grow into galaxies, stars, and the complex structure of the universe. And in the midst of these irregularities, researchers discovered something even stranger: a subtle alignment, a faint twist in the distribution of those ripples. They called it the axis of evil. This mysterious pattern suggests that the entire universe on the largest scales might have had a preferred direction of rotation, a subtle cosmic spin that began in the earliest moments and shaped the formation of everything that came after. Now, this discovery raises a tantalizing possibility. Could the universe itself have started with a rotation? Could this rotation have been imprinted into the very fabric of space-time itself? Some scientists believe that the axis of evil could be evidence of this, a leftover trace from the first cosmic spin. But how did this rotation begin? How did the universe go from a hot, dense singularity to a spinning cosmos? The answer may lie in quantum fluctuations, the tiny random changes in energy that occurred when the universe was smaller than an atom. Even in a vacuum, these fluctuations are a constant rippling through space, creating subtle twists and turns. As the universe expanded during the period of cosmic inflation, these tiny fluctuations were stretched and amplified, growing into the vast structures we observe today. This theory, known as the first cosmic spin inflation theory, proposed by physicist Alan Guth in 1981, suggests that the rapid expansion of the universe during the first few moments after the Big Bang could have created the first hints of rotational motion. The stretching of space itself could have turned those initial quantum jitters into swirling motions that set the entire universe spinning. In the years since Guth's theory, researchers have discovered even more evidence of this primordial spin. Data from the Planck and BIC EP2 experiments suggest that during inflation, subtle rotational modes, known as B modes, may have existed in the primordial gravitational waves. These tiny curls in space-time could be the fossil record of the universe's first rotation. The Big Bang, it turns out, was not just an explosion. It was a twisting birth, an imprint of rotation that would define everything that followed. The evidence for this first cosmic spin doesn't stop there. As the universe expanded and cooled, matter began to form. First quarks and gluons, then protons and neutrons, and eventually atoms. And with each step, each new level of complexity, that ancient spin was passed along. Just like a figure skater pulling in her arms and spinning faster, every new formation in the universe inherited the angular momentum of the first rotation. This law of conservation of angular momentum, motion must come from motion, was at play from the very beginning. The universe didn't have to learn to rotate. It was born with a spin already in place. And even today, that spin is still with us. Galaxies, stars, planets, all continue to rotate, each carrying a piece of that ancient momentum. When we look at distant galaxies, we can see that their rotation patterns are not random. They show subtle preferences for one direction or another, an imbalance in the universe's spin that could trace all the way back to the first moments after the Big Bang. One of the most intriguing discoveries in this regard came in 2011, when researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies. They found a subtle preference in the direction of their rotation, an imbalance that could be a direct legacy of the universe's first spin. This handedness of the cosmos, galaxies spinning in one direction more often than the other, could be a lingering imprint of that primordial rotation. Even dark matter, that invisible substance that makes up most of the universe's mass, could carry a spin signature. Simulations by NASA's Jet Propulsion Laboratory suggest that dark matter halos twist and rotate, guiding galaxies through space like whirlpools. Without that rotation, galaxies would tear themselves apart. The early universe, it seems, set everything spinning. And that spin is still keeping the stars in balance. Yet, despite all the evidence, the question remains: who or what began the spin? How did that first rotation get started? The answer, scientists believe, lies in the breaking of symmetry. In the earliest moments after the Big Bang, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. But as the universe cooled and expanded, those forces began to separate, breaking the symmetry that had existed at the moment of creation. It was this broken symmetry that allowed motion to begin. In a perfectly balanced universe, nothing could move. But when that balance was disturbed, everything came to life. The tiny imperfections in the early universe, fluctuations in energy, slight differences in temperature, were the seeds of all the motion we see today. And in those first moments, that disturbance, that break in symmetry, set everything in motion, causing the universe to begin its eternal spin. So when we ask who set the universe spinning, the answer might be simpler than we think: the universe itself. It was born spinning, from the moment of its birth. And the evidence of that spin is written into everything we see today. Take a breath and remember this: the motion you feel, the rhythm of time, the turning of the earth and the stars. It's not random, it's the echo of the first spin, the continuation of a motion that began long before our sun was born. The universe was never still. It has always been in motion, and that motion is part of the fabric of everything. As we venture further into the mysteries of the universe, we now face a crucial question: did spinning make life possible? This question isn't just about the motion of celestial bodies, nor is it confined to the cold and distant galaxies. No, this question hits much closer to home. It's about us, about Earth, and about the very reason life exists here at all. Could the simple act of spinning, of motion itself, be responsible for the incredible balance and complexity that sustains life on our planet? Without rotation, Earth would be a dead world, silent, frozen, a barren rock drifting endlessly through space, trapped in a perpetual cycle of day and night, with one side scorched by the unrelenting heat of the sun, and the other locked in eternal darkness. No movement, no change, no life, but because Earth spins, it breathes. The planet is alive, not just in the biological sense, but in a fundamental way. Rotation drives the very heartbeat of the planet, creating the day-night cycle that regulates the environment and stabilizes the climate. The planet's motion keeps the atmosphere circulating, the oceans flowing, and the landforms constantly shaped by wind and water. Without that spin, the planet would be a lifeless desert, unable to sustain the rich diversity of ecosystems we know today. Let's explore how Earth's rotation contributes to the conditions that allow life to flourish. The first and most obvious effect of the planet's spin is the alternation of day and night. The Earth rotates on its axis, completing one full rotation every 24 hours. This cycle brings sunlight to different parts of the planet, creating the temperature variations that drive weather systems and sustain life. If the Earth didn't rotate, there would be no day or night, just a constant, unchanging landscape of extreme temperatures, with one side of the planet burning in the sun's heat and the other frozen in the endless night. The rotation of the Earth is responsible for the shifting of winds, the movement of ocean currents, and the patterns of rainfall that give rise to different climates across the globe. This dynamic system of air and water circulation is known as the Coriolis effect, and it is one of the most fundamental drivers of the Earth's weather systems. Without the Coriolis effect, there would be no hurricanes, no trade winds, and no ocean currents. The atmosphere would become stagnant, and weather patterns would collapse into chaos. Life, as we know it, would be impossible. Another crucial benefit of Earth's rotation is the creation of the planet's magnetic field. Beneath our feet, deep within the Earth's core, the motion of molten iron and other metals creates the planet's magnetic field. As the Earth spins, it generates a powerful magnetic dynamo that shields the surface from the harmful effects of solar radiation. This magnetic field acts as a protective shield, deflecting harmful particles from the sun and preventing them from stripping away the atmosphere as they did on Mars. Without this magnetic shield, the solar wind would gradually erode the Earth's atmosphere, making it impossible for life to survive. In fact, Mars, which has a weaker magnetic field due to its lack of planetary rotation, is a desolate, lifeless world with no atmosphere to speak of. The Earth's rotation not only keeps the planet's atmosphere intact, but also ensures that life has a safe environment in which to evolve and thrive. But Earth's rotation doesn't just protect us from cosmic threats, it also creates the conditions that support life. One of the most vital effects of Earth's rotation is its impact on the planet's climate. Because the Earth is tilted on its axis, the angle at which the sun's rays strike the surface changes throughout the year, creating the seasons. The variation in sunlight exposure, combined with the planet's rotation, generates temperature gradients that drive the movement of air and water. These gradients, in turn, create the weather systems and ecosystems that sustain life. Without this delicate balance, Earth would be a very different place. A planet with no seasons, no cycles of temperature change, and no variability in climate. Instead, we would live in a static world, where nothing ever changes, where ecosystems remain locked in place, unable to adapt to new conditions. Life would not have had the opportunity to diversify or evolve. Rotation also plays a crucial role in the planet's biological rhythms. All life on Earth has evolved to synchronize with the Earth's 2-4-hour day-night cycle. From the smallest microbe to the largest mammal, living organisms are tuned to the rhythm of the Earth's rotation. This internal clock, known as the circadian rhythm, regulates everything from sleep-wake cycles to the timing of cellular processes. Plants, animals, and even bacteria all rely on this daily rhythm to function properly. The circadian rhythm is so ingrained in life on Earth that even without sunlight, organisms will continue to follow a roughly 2-hour cycle. For example, studies have shown that in complete darkness, the internal clocks of certain organisms will still follow a 2-4-hour cycle, demonstrating that life itself is fundamentally linked to the rotation of the planet. Without this rhythm, biological systems would break down and life would be unable to function. The Earth's spin has also influenced the development of life in another profound way: the formation of the Moon. Billions of years ago, a Mars-sized object, Theia, collided with the young Earth, sending debris into orbit that eventually coalesced into the Moon. This cataclysmic event not only created our Moon, but also had a significant impact on the Earth's rotation. The collision increased the Earth's spin, shortening the length of a day from about 6 hours to the 2-4-hour cycle we have now. Over time, the gravitational pull of the Moon has been slowly slowing the Earth's rotation, transferring angular momentum to the Moon. This process is still happening today, and the Moon is slowly drifting away from the Earth at a rate of about 1.7 centimeters per year. This interaction between the Earth and the Moon is a delicate balance that helps stabilize the planet's rotation and maintain the conditions that support life. As the Earth's rotation slows, the length of the day gradually increases. In fact, scientists have discovered that the Earth's day is getting longer, albeit at a very slow rate, about 1.7 milliseconds per century. This may not seem like much, but over millions and billions of years, this change could have significant effects on the planet's climate and ecosystems. The Moon's influence on the Earth's rotation is a reminder that the conditions necessary for life are constantly changing, even as the planet continues to spin. As we look beyond our own planet, we see that rotation plays a similar role on other worlds. Jupiter, for example, is the fastest rotating planet in the solar system, completing a full rotation every 9 hours and 56 minutes. This rapid spin drives the planet's ferocious winds and massive storms, including the Great Red Spot, a hurricane larger than Earth that has raged for centuries. The rotation of Jupiter shapes its atmospheric dynamics and contributes to its unique banded appearance. Venus, on the other hand, rotates extremely slowly. One full rotation takes about 243 Earth days. Even more strange, Venus rotates in the opposite direction of most other planets, including Earth. This backward rotation, combined with its thick atmosphere, creates a runaway greenhouse effect, trapping heat and making Venus the hottest planet in the solar system. The relationship between rotation and habitability is clear. A planet's rotation directly impacts its climate, weather patterns, and the overall stability of its environment. Without rotation, a planet cannot support life as we know it. The Earth's rotation is not just a physical movement, it is a fundamental part of the delicate balance that sustains life on our planet. In the search for habitable exoplanets, scientists are looking for planets that exhibit similar characteristics to Earth, planets that rotate on their axes and experience day-night cycles. These planets are more likely to have stable climates, protected atmospheres, and the conditions necessary for life to thrive. The search for these worlds is ongoing, with NASA's Kepler mission and the James Webb Space Telescope working to identify exoplanets that may have the right conditions for life. As we explore the mysteries of the universe, we are reminded of the profound role that rotation plays in our existence. Without it, life as we know it would be impossible. The spinning of Earth, the turning of the galaxies, and the rotation of atoms all contribute to the intricate dance that sustains the universe. And as we look to the stars, we know that life's existence is inextricably linked to the rhythm of the cosmos itself. Take a moment to reflect on this cosmic dance. The rotation of the Earth, the movement of the stars, the shifting of the tides, all of it is part of a grand symphony that has been playing for billions of years. And as long as the Earth continues to spin, life will continue to thrive, evolving in harmony with the motion of the universe. Now that we've explored the profound impact of rotation on life, let's delve deeper into another extraordinary concept. Can rotation bend time itself? This idea, which may sound like something out of a science fiction story, is not only grounded in reality, but also represents one of the most captivating and verified aspects of modern physics. Rotation, it turns out, does more than just move matter. It distorts the very fabric of time and space. It's time to address a question that pushes the boundaries of our understanding. What happens when rotation reaches extreme speeds? When you think of time, you likely think of it as a constant, moving forward in a linear, predictable fashion. But rotation, when it reaches the right speed and intensity, can change how we experience time itself. The faster an object spins, the greater its effect on the curvature of space-time, and the more it bends the flow of time. This concept was first predicted by Albert Einstein in his theory of general relativity, which was published in 1915. Einstein's theory tells us that gravity and motion are inseparable. Both are a result of the way mass curves space-time. The more massive an object, and the faster it spins, the more it distorts the geometry of space and time. This twisting of space-time is known as frame dragging, a phenomenon that may sound abstract, but has been demonstrated in the most precise and elegant ways. Imagine space-time as a calm, undisturbed lake. When a massive object such as Earth or a black hole begins to spin, it stirs this lake, creating tiny vortices, ripples in the very flow of time itself. These vortices affect the direction of time. In other words, when space itself is twisted, the flow of time can bend along with it. NASA's Gravity Probe B experiment, launched in 2004, aimed to confirm Einstein's predictions. The spacecraft carried 4 ultra-sensitive gyroscopes that measured the tiny shifts in the direction of spacetime as the Earth rotated. After a year of precise measurements, the data confirmed Einstein's theory. The Earth's rotation drags spacetime ever so slightly, about 0.000011 degrees per year. While this effect is incredibly small, it matches Einstein's equations with extraordinary precision, and it reveals that even Earth's gentle rotation, occurring every 24 hours, is capable of bending the flow of time. But what happens when the rotation speeds up? When the object becomes far more massive? What happens when the speed of spin increases exponentially, reaching the extraordinary velocities seen in the most extreme environments of the cosmos? This is where the mysteries of the universe truly unfold. Take, for instance, neutron stars, the remnants of massive stars that have collapsed under their own gravity. These stellar remnants are incredibly dense, with a mass greater than the Sun packed into a space just about 12 miles in diameter. To conserve angular momentum, these stars spin at incredible speeds, up to 700 times per second. When these stars collapse, they create some of the most extreme gravitational fields in the universe. The forces at play here twist and distort space-time so violently that even light struggles to travel in straight lines. The magnetic fields of neutron stars, called pulsars, are so intense that they create beams of radiation, which sweep across space like cosmic lighthouses. As these beams rotate, they reveal the most extreme effects of time dilation. Time near a pulsar slows dramatically compared to time on Earth. For every second that passes near a pulsar, minutes or even hours may pass for an observer on Earth. This is gravitational time dilation, a key prediction of Einstein's theory. As you approach these extremely massive, rapidly rotating stars, time itself begins to slow down, proof that rotation can indeed bend time. Yet the most astonishing example of this phenomenon lies in the heart of a black hole. Black holes, the most mysterious and powerful objects in the universe, possess the most extreme gravitational fields known to science. And when a black hole is rotating, its gravitational influence becomes even more profound. These spinning black holes, known as Kerr black holes, twist space and time so violently that they create a region near their event horizon called the ergosphere. The ergosphere is a zone where no object, not even light, can remain stationary. The closer you get to the event horizon, the stronger the pull becomes, and time itself begins to stretch and bend. In 2021, NASA's Chandra X-ray Observatory captured images of a black hole at the center of the galaxy M87. The images revealed how matter spirals into the black hole, creating a glowing, spinning accretion disk around it. The light from this matter is twisted by the intense curvature of space-time, and the time it takes for light to escape from the black hole's vicinity. The phenomena of time dilation around rotating objects are not just theoretical. This is a real effect that we can observe and measure. For example, even on Earth, satellites orbiting the planet experience a slightly different passage of time than clocks on the surface. This difference, although minute, is due to the combination of two factors: the motion of the satellites and the gravitational field of the Earth. The satellites are moving faster than objects on the surface, so they experience time more slowly according to the theory of relativity. In addition, they are further away from Earth's gravitational pull, which causes them to experience less time dilation than objects on the surface. This is why, when we use systems like GPS, the timing on the satellites must be adjusted to account for these differences. If we didn't take these slight time discrepancies into account, navigation systems would drift, and over time they would be inaccurate by miles. What is perhaps most mind-bending about this entire concept is the realization that rotation itself can alter the fabric of time. The faster the rotation, the more the distortion, and as we approach the event horizon of a black hole, the rotation twists space-time to such an extreme that time itself is fundamentally warped. It's not just a matter of speeding up or slowing down. It's a radical redefinition of what time is, how it flows, and how we experience it. The very fabric of space and time, once considered stable, is now shown to be malleable and subject to the whims of motion. At the highest levels of spin, we encounter one of the most perplexing and awe-inspiring phenomena in the universe: closed time-like curves. These are paths in space-time that, theoretically, could allow for time travel. If the rotation of a black hole, or any other extremely fast-spinning object, distorts space-time enough, it's conceivable that a particle could travel along a closed path that loops back to its earlier position in time. While this concept remains purely theoretical and not yet experimentally verified, the possibility that rotation could create such loops is one of the most profound implications of Einstein's general theory of relativity. This concept stretches beyond just theoretical physics and touches on deep questions about the nature of time, space, and our place in the universe. If time can be bent, and if rotation is a key driver of that distortion, then we are forced to ask ourselves, how much control do we truly have over time? Is it an immutable force? Or is it just another dimension, shaped and molded by the forces of the universe? The consequences of these questions extend far beyond black holes and neutron stars. As our understanding of space-time deepens, we begin to see that the universe's very structure is a delicate interplay of motion and time. Rotation, at every scale, from the quantum level to the cosmic, is not just a property of matter, it's a defining feature of the universe itself. As we continue our journey, let us ask, what does this mean for us? What does it mean that we too are part of this grand dance of time and motion? In the next chapter, we will explore the profound implications of these concepts. As rotation bends time, could it also shape the very nature of life itself and the path we walk through this cosmos? Take a moment to reflect. You are part of this dance, part of this grand cosmic rhythm. Every spin of your body, every turn of your mind is connected to the infinite rotation that shapes the universe. And as we look deeper into the fabric of reality, we begin to glimpse the mystery that awaits us. The Earth's rotation is far from a passive feature. It is an active and powerful force that not only shapes the physical world, but plays an essential role in sustaining life. The cycle of day and night, the rhythm of the seasons, and the stability of the planet's magnetic field all rely on the Earth's steady spin. If the Earth did not rotate, the conditions necessary for life as we know it would simply not exist. The most immediate impact of the Earth's rotation is the alternation between day and night. This cycle is essential for life, from the plants that rely on sunlight to produce energy, to the animals that depend on this cycle for feeding, resting, and reproducing. The Earth's rotation ensures that sunlight is evenly distributed across the planet's surface, preventing one side from being scorched in perpetual daylight, while the other is locked in eternal darkness. Without this cycle, one half of the planet would be too hot to sustain life, while the other half would be too cold. The rotation of the Earth also influences the planet's weather systems and climate. As the Earth spins, it creates temperature differences between the equator and the poles, driving the movement of air masses and ocean currents. These currents help regulate global temperatures, distribute heat, and bring necessary moisture to different parts of the planet. Without the rotation, there would be no wind, no weather patterns, and no movement of the oceans, making it impossible for ecosystems to function as they do now. Rotation also plays a vital role in maintaining the Earth's magnetic field. Deep within the Earth's core, molten iron moves and churns, generating a magnetic field that shields the planet from harmful solar radiation. This magnetic field is essential for life on Earth, as it prevents solar winds from stripping away the atmosphere and exposing the surface to dangerous levels of radiation. The movement of molten iron in the core is influenced by the Earth's rotation, ensuring that the magnetic field remains stable and protective. But the Earth's rotation does more than just regulate temperature and provide a protective magnetic shield. It is also responsible for the dynamic cycles of tides that shape coastal ecosystems. The Moon's gravitational pull on the Earth's oceans causes the water to bulge and recede, creating the tides that we see every day. These tides play a crucial role in many ecosystems, especially those along the coasts, where they bring in nutrients, support biodiversity, and shape the movement of marine life. The relationship between the Earth's rotation and the Moon also affects the stability of the planet's axis. The Moon helps to stabilize the tilt of the Earth's axis, preventing extreme fluctuations in the planet's climate. Without the Moon's gravitational influence, the Earth's tilt could vary dramatically, leading to unpredictable and extreme weather patterns. This stability is essential for long-term habitability, as it keeps the Earth's climate relatively stable and allows life to thrive. In addition to all these physical effects, the Earth's rotation influences biological life on a more intimate level. Most living organisms, from plants to animals, have evolved to synchronize their internal clocks with the rhythm of the Earth's rotation. This synchronization allows for efficient processes, such as the timing of plant growth, animal migration, and human sleep patterns. The Earth's rotation has led to the development of circadian rhythms, the natural 2-4-hour cycles that regulate our body's biological processes. Disrupting these rhythms, such as by traveling through different time zones or working irregular hours, can lead to health problems, showing just how deeply connected life on Earth is to the planet's steady spin. But Earth's rotation is not a feature that will last forever. Over time, the Earth's rotation is gradually slowing down, a process that is caused by the gravitational interactions between the Earth and the Moon. This slowdown is so subtle that it can be measured only in milliseconds per century, but over millions and billions of years, it will have a profound impact on the planet. Eventually, the Earth's day will stretch longer, and the Moon will drift farther away from the planet, changing the dynamics of tides and the length of days. Even now, the Moon is moving away from the Earth at a rate of about 1.5 inches per year, and the length of a day is increasing by 1.7 milliseconds per century. While these changes are imperceptible in the short term, they will eventually reshape the rhythm of life on Earth. The relationship between the Earth and the Moon is a delicate one. The two bodies have been locked in a cosmic dance for billions of years, with the Moon's gravity influencing the Earth's rotation and the Earth's rotation slowing the Moon's orbit. This gravitational interaction has shaped the planet's tides, stabilized its tilt, and ensured that life could evolve in a stable and predictable environment. If this delicate balance were disrupted, the consequences for life on Earth could be severe. When we look at other planets in the solar system, we see that rotation plays a similar role in shaping their environments. Jupiter, for example, has the fastest rotation of any planet in the solar system, completing one full rotation every 9 hours and 56 minutes. This rapid spin drives the planet's massive storm systems, including the famous Great Red Spot, which has been raging for centuries. Similarly, the slow rotation of Venus, which takes 243 Earth days to complete one rotation, has created a runaway greenhouse effect, making the planet the hottest in the solar system. The way rotation shapes a planet's environment is not limited to its physical processes. It extends to the way life evolves on those planets. The length of a planet's day, the tilt of its axis, and the speed of its rotation all play a role in determining whether life could exist on that world. Planets with slower rotations, like Venus, have extreme temperatures, while planets with faster rotations, like Jupiter, experience chaotic storm systems. The Earth's 2-4-hour cycle strikes the perfect balance, providing a stable environment that allows life to thrive. As we look beyond our planet, we see that the concept of rotation is not limited to the planets of our solar system. Stars, too, rotate, and their rotation has a profound impact on their structure and life cycle. When stars form, they begin to spin faster as they collapse under gravity, conserving angular momentum. This spin generates magnetic fields that shape the star's behavior, influencing everything from its energy production to its eventual death. In the final stages of a star's life, when it has exhausted its fuel, it may collapse into a neutron star or a black hole, both of which rotate at incredible speeds. These extreme forms of rotation generate powerful gravitational forces that bend the fabric of space-time, warping time itself. Even on the grandest scales, rotation shapes the universe. Galaxies, including our own Milky Way, spin in vast spirals, carrying billions of stars and planets with them. The rotation of galaxies helps to distribute matter and energy across the universe, creating the cosmic structures we see today. Without this rotation, the universe would lack the dynamic structures that give rise to stars, planets, and ultimately life. At the most fundamental level, rotation is the force that governs the behavior of everything in the universe. From the spinning of electrons inside atoms to the vast rotation of galaxies, this fundamental principle shapes the nature of reality itself. As we look to the future, we begin to ask, what would happen if the universe itself stopped spinning? Would life cease to exist? Would time come to a standstill? These are the mysteries that we will explore in the next chapter as we continue our journey through the cosmos. As we dive deeper into the fabric of the universe, we encounter a question that has intrigued scientists and philosophers alike. What would happen if the universe itself, the very cosmos that has been spinning for billions of years, were to stop? Could it simply come to a standstill? Or would there be more subtle and profound consequences? If rotation defines the universe's rhythm, what happens when that rhythm falters? We begin by considering the nature of motion itself. Motion is a fundamental aspect of our existence. Everything we observe in the universe, every star, planet, and particle, is in motion. The rotation of the Earth, the revolution of planets around stars, and the spiral dance of galaxies across the cosmos are all manifestations of this fundamental principle. Without motion, the universe would lose its structure, its energy, and its life force. In many ways, motion is the heartbeat of the universe, a pulse that drives everything, from the formation of stars to the evolution of life. Now, let's imagine a universe that has stopped spinning. If we think of the universe as a vast cosmic clockwork, the cessation of rotation would be akin to a clock's gears grinding to a halt. The galaxies that have been spinning gracefully for billions of years would cease their spirals, the stars would no longer move in their orbits, and the planets would lose their momentum, drifting aimlessly through space. The very fabric of space-time itself would be affected, as it is inextricably tied to the motion of celestial bodies. Without the forces of motion and rotation, the delicate balance that sustains the universe would collapse. At a cosmic level, rotation serves as the force that organizes matter. It shapes the way galaxies are formed, influences the behavior of stars, and even affects the distribution of dark matter across the universe. The spin of galaxies, for example, plays a crucial role in the way stars and planetary systems are arranged. When galaxies spin, they generate gravitational forces that pull matter inward, causing the formation of stars and planets. Without this motion, matter would be distributed evenly, unable to condense and form the structures that make up the universe. The very fabric of the cosmos would be homogeneous, lifeless, and devoid of the complexity we observe today. On a more personal level, the idea of a universe at rest challenges our understanding of time itself. Time, as we know it, is inextricably linked to motion. It is a measurement of change, of events unfolding in a specific order. The rotation of the Earth defines our concept of a day, while the movement of the planets around the Sun creates our year. Time is not a separate entity, but a direct result of the motion of celestial bodies. Without motion, time would lose its meaning. If the universe were to stop spinning, time, as we experience it, would cease to exist. There would be no future, no past, only an endless, frozen present. Yet there is a paradox at the heart of this question. As we have seen, rotation is not merely an external force that shapes the cosmos. It is woven into the very fabric of existence. The particles that make up matter, the protons, neutrons, and electrons, are all in motion. At the quantum level, this motion is not just a physical phenomenon, but a fundamental aspect of the particle's existence. Each particle carries an intrinsic angular momentum, or spin, that is independent of the macroscopic motion of celestial bodies. In this sense, even if the large-scale rotation of galaxies and stars were to cease, the universe would not be entirely at rest. The quantum spins of particles would continue, preserving the flow of time on a microscopic level. This idea brings us to a profound realization. Even in a universe at rest, motion would persist. It might be invisible, operating on scales too small for our senses to detect, but it would still exist. This motion, although imperceptible to the human eye, would continue to shape the universe at its most fundamental level. The rhythm of the cosmos would continue, not through the rotation of galaxies, but through the motion of particles that make up every atom, every molecule, and every living organism. Even the forces that govern the universe, gravity, electromagnetism, and the strong and weak nuclear forces, are fundamentally linked to motion. Gravity, for instance, is the result of the curvature of space-time caused by the presence of mass. This curvature is directly tied to the motion of massive objects, such as stars and planets. The electromagnetic force, which governs the behavior of charged particles, is also a manifestation of motion. The electric and magnetic fields that define this force are constantly in motion, oscillating and interacting with each other. Without this motion, the universe would not be able to function as it does. It would be a static, lifeless place, incapable of sustaining the complexity and beauty we observe. In essence, the cessation of the universe's large-scale motion would not mark the end of all motion. Instead, it would signal a shift in the way motion is expressed. The macroscopic rotation of galaxies and stars might slow down or cease, but the microscopic motion of particles would continue, preserving the very fabric of existence. This suggests that motion is not just a result of external forces, but an intrinsic property of the universe itself, a force that cannot be easily undone. However, the idea of a universe without motion raises other questions about the future of the cosmos. If the universe were to reach a state of perfect stillness, what would happen to the structures that have formed over billions of years? Would galaxies lose their shape and collapse? Would stars stop shining and fade into darkness? These are questions that physicists and cosmologists continue to explore as they seek to understand the ultimate fate of the universe. One possibility is that the universe could eventually reach a state known as heat death. This is a condition in which the universe has expanded so much that all energy is evenly distributed. There would be no temperature differences, no gradients of energy, and no forces to drive motion. In such a scenario, the universe would become a cold, dark, and lifeless expanse, with no stars, no galaxies, and no events to mark the passage of time. In this state, even the smallest motions of particles would gradually slow down, and the universe would cease to change. It would be a place of perfect stillness, where nothing happens. But even in this extreme scenario, motion would not be entirely absent. The fundamental forces of nature would still operate on the smallest scales, ensuring that the universe continues to evolve, even if imperceptibly. The quantum fluctuations that give rise to particles, the motion of atoms and molecules, and the interactions between forces would persist, albeit in a vastly diminished form. In this way, the universe would continue to remember its motion, even in the face of stillness. This leads us to a fascinating question. If the universe's motion is eternal, what happens when everything comes to an end? If the stars burn out and the galaxies fade, will the universe retain its memory of motion? Will the echoes of its spin continue to reverberate across the cosmos, leaving behind traces of the motion that once was? And if the universe eventually reaches a state of perfect stillness, will time itself lose its meaning? These are the mysteries that continue to captivate our imaginations as we search for the ultimate understanding of the universe. In the next chapter, we will explore the concept of time itself and its relationship to motion. How does time flow in a universe where everything is in motion? What happens to time when motion slows down or stops? Join me as we journey further into the heart of the cosmos, where the answers to these questions may hold the key to understanding the very nature of existence. As we journey deeper into the mysteries of time and motion, we must confront one of the most perplexing concepts in all of physics. What happens to time itself when motion slows down? When the universe loses its rhythm, when the heartbeat of existence begins to fade, does time cease to flow as we know it? To truly understand this, we must first recognize that time, as we perceive it, is inextricably tied to the motion of objects in the universe. Time flows because things move, planets revolve, stars burn, particles collide, and galaxies spin. These movements, large and small, create the ticking clock that defines our existence. But what happens when that motion slows, or worse, stops altogether? To begin answering that question, let us consider the concept of time dilation, a phenomenon predicted by Albert Einstein in the early 20th century. According to his theory of relativity, time does not flow at a constant rate across the universe. Instead, time is affected by both gravity and motion. The faster you move, the slower time passes for you relative to someone who is at rest. Similarly, the closer you are to a massive object, such as a planet or a black hole, the slower time will move for you, compared to someone far away from that mass. This effect, known as time dilation, has been confirmed through numerous experiments and observations, including the famous Hafele-Keating experiment, where atomic clocks on airplanes moved at different speeds and showed measurable differences in the passage of time. So, What does this mean for a universe that is slowing down? As the cosmic expansion continues and galaxies drift further apart, the universe is losing its momentum. The movement of matter is gradually slowing, and with it, the rate at which time passes. If the universe reaches a point of perfect stillness, where everything has come to rest, will time cease to exist altogether? This is a question that stretches the limits of our understanding. According to the laws of physics, time is a dimension, just like space. It is woven into the fabric of the universe, shaping and being shaped by the movement of matter and energy. But time, like space, is not a fixed entity. It can stretch and compress, slow down or speed up, depending on the conditions around it. In a universe where motion has come to an end, time may become a frozen, static entity, a dimension devoid of any change, progression, or flow. Yet there's a catch. Even in a universe that has reached the limits of motion, time may not disappear entirely. It may become frozen, but not in the way we might expect. Imagine a universe where all matter has slowed to a crawl. In this state, motion still exists at the most fundamental levels, at the level of atoms and particles. Even though galaxies have ceased their spin and stars have burned out, the particles that make up the very fabric of reality would still retain some form of motion. These quantum fluctuations, though subtle, would continue to preserve the passage of time on a minuscule scale. This motion, however imperceptible, would serve as a kind of memory of the universe's once great rhythm. In fact, even when the universe reaches this distant, silent state, the laws of physics may continue to operate on the smallest scales. Quantum mechanics tells us that even in a vacuum, particles continue to move in a process known as quantum fluctuations. These fluctuations are responsible for the creation and annihilation of particles in what is known as a quantum foam. So, even in a universe where the large-scale motion has stopped, time may persist at a quantum level, governed by the uncertainty inherent in quantum systems. But how does this tie into the concept of life itself? What does the slowing down of the universe's motion mean for the biological systems that depend on motion to sustain life? As we've seen, rotation, motion, and time are deeply intertwined. The Earth's rotation defines our days and nights, drives our weather systems, and sustains life on Earth. Without motion, the very conditions that support life would collapse. If the universe were to slow down to the point where motion ceases, would life as we know it still be possible? This is where we encounter a paradox. Time, as we experience it, is bound to the motion of the universe. Life as we understand it is a process that relies on motion, biological systems that depend on the flow of energy, the circulation of blood, the movement of particles within cells. If all motion were to cease, life would no longer be sustainable. The atoms and molecules that make up living organisms would no longer interact in the way they do today. Biological processes would grind to a halt. In essence, if the universe's motion slows to a standstill, the very essence of life itself may fade away. But does this mean that the universe's fate is sealed? Are we destined to witness a gradual march toward eternal stillness? Not necessarily. While the universe is indeed slowing down, it is also expanding. The forces at play are not uniform, and the energy of the universe is not evenly distributed. There are still pockets of activity, regions of space where new stars are being born, where galaxies continue to collide and evolve. Even as some parts of the universe lose their energy, others are still in the process of creating, giving birth to new structures and new forms of motion. This dynamic tension between the slowing of the universe and the emergence of new forces creates a fascinating cosmic dance. It's as if the universe is always teetering between stillness and movement, decay and creation. Even in the farthest reaches of space, new possibilities are unfolding. Supernovae explode, new stars are formed, and black holes twist space and time. Even as the universe ages and its overall motion slows, there is still the potential for new forms of activity, new pockets of life, and new ways of perceiving time. In a sense, This reflects the cyclical nature of existence itself. Life, in all its forms, depends on cycles, whether it's the cycles of the seasons, the rhythms of our heartbeats, or the rotation of the Earth. The universe, too, has its cycles. While the current cycle may be one of slow decline, it is possible that the universe will one day experience a rebirth, a new era of creation that brings about new rhythms of motion and time. This would not be a simple return to the past, but a reinvention of what it means to exist, to move, and to experience time. Ultimately, this question of what happens when the universe slows down is not just a scientific one, it's a philosophical one. It forces us to confront the very nature of existence and what it means for us to be part of this vast, ever-changing cosmos. What happens when the rhythm of the universe fades? Does time lose its meaning? Or is time itself a reflection of the motion that permeates the universe? And as we approach the end of the universe's life, what role will we play in this grand cosmic story? In the next part, we'll delve deeper into this question and explore the potential for a new beginning. Can the universe be reborn even after it has reached the end of its current cycle? What does the future hold for the cosmos and for us as we continue our journey through the stars? As we continue our exploration, let's turn our attention to one of the most profound concepts in cosmology: the fate of the universe itself. For centuries, astronomers have wondered how the universe will end. We've seen its beginnings, how everything emerged from a single, unimaginable point of singularity. But what of its end? The universe has been expanding since the Big Bang, and its expansion is still ongoing. But as we've learned, the very forces that have propelled it outward may ultimately lead to a contraction. In other words, everything that expands must one day collapse, right? This cosmic dance between expansion and contraction brings us to one of the most debated theories in modern physics: the possibility of the universe's eventual Big Crunch. The Big Crunch hypothesis suggests that the universe's expansion, which has been accelerating due to dark energy, will one day slow down. Over billions of years, as gravity pulls matter back together, galaxies, stars, and even planets could be drawn toward one another. In the end, everything, every star, every galaxy, and every atom, could collapse back into a single point, where the laws of physics, as we understand them, might break down entirely. But this idea, while fascinating, is far from settled. In fact, it's one of the most significant questions facing cosmologists today. If dark energy, the mysterious force causing the accelerated expansion of the universe, continues to dominate the cosmos, it may prevent a big crunch altogether. Instead, the universe could expand indefinitely, forever growing colder and more distant, leading to a state known as the heat death of the universe.
Imagine a universe where galaxies are so far apart that even light from one galaxy would never reach another.
All stars would eventually burn out, leaving behind only black holes and dead remnants of once thriving cosmic bodies. In this scenario, time itself would be marked by the slow, steady decay of energy, with the universe slowly becoming colder and darker as it drifts further from its once glorious birth. The heat death scenario highlights the inevitable consequences of entropy, the second law of thermodynamics, which states that energy naturally tends to disperse over time, moving toward a state of maximum disorder. It's an uncomfortable thought, the eventual heat death of everything we know and love, a universe where motion stops, and time, as we experience it, fades away. But let's step back from the final moments of the universe and consider what happens before we reach that point. The universe has been expanding for billions of years, and in that time it has created a stunning array of structures, from the tiniest atoms to the vastest galaxies. And though the cosmos may eventually reach its limit, we are still in the midst of a vibrant, unfolding story. In fact, there is still much we do not know about the universe's true nature and how it will evolve. One of the most exciting areas of research today is the study of dark matter and dark energy, two invisible forces that make up nearly 95% of the universe's total mass energy content. These forces shape the structure of the universe, influencing everything from galaxy formation to the expansion rate itself. Yet, despite decades of research, scientists still have little idea what dark matter and dark energy actually are. Could they hold the key to the universe's fate? What we do know is that dark energy, which is responsible for the accelerating expansion of the universe, may continue to drive this expansion indefinitely. In this scenario, the universe will stretch out so thinly over time that even the most massive galaxies will be so far apart that they will become invisible to each other. The night sky, once filled with stars and galaxies, would eventually be empty. The universe's cooling would lead to a time when not even black holes could emit energy through Hawking radiation, leaving behind only the faintest traces of the cosmos's once vibrant activity. But is there a possibility that the universe's expansion could slow down? Could gravity eventually overpower dark energy, leading to a contraction? The answer to this question hinges on a key factor: the total mass and energy content of the universe. Scientists have been carefully measuring the density of the universe, the total amount of matter and energy in a given volume of space. If the universe's density is greater than a certain threshold, gravity could eventually slow the expansion, causing everything to collapse back inward in a big crunch. However, if the density is too low, the universe will continue to expand forever. We've been able to observe the universe's expansion in remarkable detail, thanks in part to the discovery of the accelerating expansion. This discovery was made in the late 1990s by two independent teams of astronomers studying distant supernovae. They expected the supernovae to be moving closer to Earth due to the gravitational pull of the matter in the universe. Instead, they found that the supernovae were accelerating away from us, driven by an unknown force. This led to the conclusion that dark energy, the mysterious force responsible for this acceleration, is working against gravity. With the discovery of dark energy, we are now facing a universe that is accelerating in its expansion. This new knowledge has shifted our understanding of the cosmos, creating a sense of urgency to understand how this mysterious force will influence the future of everything. It is also raising questions about the ultimate fate of the universe itself. Will dark energy eventually overpower the gravitational pull of matter, driving everything apart in a cold, endless expansion? Or will there be a reversal as gravity prevails and forces the universe to collapse? For now, the fate of the universe remains an open question. The data we have today points toward an expanding, cooling universe, but the ultimate outcome depends on forces that we do not yet fully understand. As scientists continue to study dark energy, dark matter, and the other forces that shape the cosmos, they will inch closer to unlocking the universe's grand mystery. But whether the universe ends in a big crunch, a heat death, or some other fate remains to be seen. As we contemplate the vastness of space and the passage of time, it is humbling to realize that we are living in the middle of this cosmic story. Our existence is but a fleeting moment in the grand history of the universe. Yet, in this brief moment, we are part of something magnificent, an ever-evolving cosmos that is constantly changing, growing, and expanding. The universe may one day reach its end, but until then, we are privileged to witness its beauty, its complexity, and its motion. As we explore these mysteries, we come to understand that the universe is not just a place we inhabit, it is a story we are part of, a story that continues to unfold before our very eyes. And no matter what the future holds, one thing is certain: the journey of the universe, with all its twists and turns, is far from over. As we continue on our cosmic journey, let us consider another question that has puzzled humanity for centuries: the nature of time itself. It is a concept so fundamental to our understanding of the universe, yet so elusive in its true nature. Time, as we experience it, flows in one direction. We are born, we live, and we die, all within the confines of a linear progression from past to present to future. But is time truly the linear, unidirectional force we perceive it to be? To answer this question, we must once again turn to the theory of relativity, specifically Einstein's general theory of relativity, which tells us that time is not a constant, unchanging force. Instead, It is intertwined with the fabric of space itself. Space and time, together, form a four-dimensional continuum known as space-time. In this model, time can be stretched and warped, depending on the presence of mass and gravity. This means that time is not an immutable constant, but rather something that can be altered by the objects and forces around us. Einstein's equations of general relativity describe how massive objects, such as stars and planets, bend the fabric of space-time, creating what we experience as gravity. But these same equations also predict that time itself is affected by gravity. Near a massive object, time slows down relative to an area of weaker gravity. This phenomenon, known as time dilation, has been confirmed by numerous experiments and observations, including those with atomic clocks placed at different altitudes and velocities. One of the most fascinating implications of time dilation is its relationship to black holes. These mysterious objects, formed when massive stars collapse under their own gravity, warp spacetime to such an extent that not even light can escape their grasp. As we approach the event horizon, the point of no return around a black hole, time itself slows down, stretching to a standstill. To an observer far away, it would appear as if time comes to a halt for anything crossing the event horizon. This strange phenomenon, known as gravitational time dilation, is one of the many mind-bending aspects of black holes. But what if time itself is not just a consequence of gravity? What if it is something more, something fundamental to the very structure of the universe? Could time have existed before the Big Bang? Before the birth of the cosmos as we know it? And if so, what did that time look like? Some scientists propose that time may have had a different nature in the very early moments of the universe, during the Planck epoch, which occurred just moments after the Big Bang. During this time, the universe was so small and dense that the laws of physics, as we understand them, may not have applied. Time in this early stage may have been indistinguishable from space, and the concept of a flowing linear progression of time may not have existed. Instead, the universe may have existed in a state of timelessness, where events and processes were not governed by the familiar ticking of the cosmic clock. This idea leads to one of the most profound questions in cosmology. Did time have a beginning? In the classical view of the Big Bang, time itself began at the moment of the universe's birth. But this raises a paradox. If time began with the Big Bang, what came before it? How can time have a beginning but no before to speak of? It is a question that pushes the boundaries of human understanding and challenges our very conception of reality. In recent years, some physicists have proposed that time, as we know it, may have emerged from a more fundamental, timeless state. This idea, known as the emergent time hypothesis, suggests that time may not be a fundamental property of the universe, but rather something that arose as the universe cooled and evolved. Just as the flow of water emerges from the interaction of individual molecules, time may have emerged from the fundamental processes of the early universe. In this view, time is not something that exists independently of the universe, but rather a product of the universe's development. As we look deeper into the mysteries of time, we are confronted with the strange and paradoxical nature of the universe itself. Time, it seems, is not as simple as we once thought. It is not just a linear progression from past to future, but a dynamic, malleable force that can be shaped by the very fabric of space-time. And as we explore the boundaries of time, we are led to new questions about the universe's origins, its evolution, and its eventual fate. But time, as it turns out, is not just a cosmic phenomenon. It is also a deeply personal one. Our experience of time, how we perceive its passage, shapes every moment of our lives. We measure our days in hours, minutes, and seconds, but these units of time are not absolute. They are human inventions created to help us navigate a world that is constantly in motion. Our perception of time is also influenced by our senses and our consciousness, which allows us to experience the flow of time in ways that are deeply subjective. This subjective experience of time is one of the most fascinating aspects of human existence. For example, as we age, our perception of time seems to change. When we are young, time appears to move slowly, with each day seeming to last forever. But as we grow older, time seems to accelerate. A year feels shorter than it did when we were children, and the days seem to pass by more quickly. Some scientists believe this phenomenon is due to the way our brains process information. When we are young, we encounter more novel experiences, and our brains store more memories. As we age, however, we become more familiar with the world around us, and our brains may process fewer new experiences, leading to the perception that time is moving faster. This subjective experience of time is not just limited to our perception of age, it also affects our sense of urgency, our decisions, and our sense of meaning. Time influences how we prioritize our lives and how we find purpose in our daily activities. It shapes our relationships, our work, and even our connection to the universe itself. And yet, for all our understanding of time, there remains one final mystery: the end of time.
What happens when time itself runs out?
Is there an ultimate conclusion to the passage of time, a moment when everything ceases to exist as we know it? As we continue our journey through the universe, we'll look ahead to this final question and ask, what happens when time itself comes to an end? As we journey further into the vast mysteries of the cosmos, we are drawn to one of the most profound questions that has haunted humanity for millennia. What happens when time itself comes to an end? What does the final chapter of the universe look like when the cosmic clock has finished ticking and all motion ceases? The concept of the end of time is one that stretches the imagination and challenges our deepest understanding of existence. In exploring this question, we must confront the possibility that time, like everything else in the universe, has a beginning, a middle, and an end. Theories abound regarding the eventual fate of time, but all of them share a fundamental insight. The universe is not eternal in the way we once believed. It is not static. It is dynamic, ever-changing, and ultimately, it will reach a point of no return. One of the most widely discussed theories about the end of time is known as the heat death of the universe. This concept arises from the laws of thermodynamics, which govern the flow of energy and the transformation of matter. According to the second law of thermodynamics, entropy, the measure of disorder, tends to increase over time. In a closed system, this means that energy becomes more evenly distributed and systems move toward a state of maximum entropy or thermodynamic equilibrium. In practical terms, this means that the universe, over an incomprehensibly long period, will slowly lose its energy, and everything will reach a state of uniform temperature. As the universe ages, stars will burn through their fuel, and the vast majority of them will die, leaving behind cold, dark remnants known as white dwarfs, neutron stars, and black holes. The galaxies will drift apart, and the space between them will grow increasingly empty. As stars fade, the process of stellar fusion will cease, and the universe will enter a phase of extreme isolation. In the end, when every source of energy is depleted, the universe will become a vast, dark, cold void. There will be no light, no motion, and no change, just a still, lifeless expanse. This state of cosmic entropy is referred to as the heat death, as it represents the ultimate end of all thermodynamic processes. In this scenario, time itself would continue to exist, but there would be no events left to mark its passage. No stars to rise and set, no galaxies to rotate, no biological rhythms to track the flow of existence. The passage of time would lose all meaning, as the universe would be trapped in a state of eternal stillness. In this way, the heat death of the universe represents the ultimate end of motion, and therefore the end of the universe as we know it. However, while the heat death is one possibility, there are others that have been proposed by cosmologists and physicists. Another leading theory is the Big Crunch, which suggests that the expansion of the universe, which has been occurring since the Big Bang, may eventually reverse itself. If the density of the universe is high enough, the gravitational pull of matter could cause the universe to collapse back in on itself. This process would lead to the collapse of galaxies, stars, and even subatomic particles, all converging into a singularity, a point of infinite density, much like the state of the universe before the Big Bang. In the Big Crunch scenario, time would come to an end not through the slow dissipation of energy, but through a cataclysmic event. The universe would collapse into a singularity, and with it all physical laws would break down. Space and time would become indistinguishable, and the very fabric of the universe would collapse into a point of infinite gravity, where the concept of time, as we understand it, would no longer hold. The Big Crunch would mark not just the end of the universe, but the end of time itself. Yet another possibility is the Big Rip, a more dramatic scenario in which the universe continues to expand at an accelerating rate due to the influence of dark energy. This expansion would cause galaxies, stars, planets, and even atoms themselves to be torn apart as the fabric of space stretches ever further. In the Big Rip model, time would not end through a slow, gradual process or a violent collapse, but through the disintegration of the very structure of reality. As the universe is torn apart at the atomic and subatomic levels, time itself would lose its coherence, as everything that relies on the passage of time, life, motion, and even the fundamental forces of nature, would cease to exist. Each of these theories presents a different vision of how the universe and time could meet their end. But regardless of the outcome, one thing is certain: time, as we experience it, is not infinite. It is a dynamic, ever-changing force that is intimately tied to the nature of the universe itself. Just as the universe was born in a moment of incredible expansion, it will one day meet its inevitable conclusion, and with it, the passage of time will come to an end, whether that means a slow fade into stillness, a dramatic collapse, or the violent tearing apart of the cosmos. As we look beyond the end of time, we are forced to confront another profound question. What does this all mean for us? If time is finite, if the universe is destined to fade into darkness or collapse into a singularity, what is the purpose of our lives, of our existence, in the grand scheme of things? The answer to this question is one that has eluded philosophers, scientists, and thinkers for centuries. Some argue that the purpose of life is to find meaning in the fleeting moments we have, to embrace the beauty of existence even in the face of inevitable decay. Others propose that the purpose of life is to seek knowledge, to understand the mysteries of the universe before it all fades away. In the end, the question of whether the universe and time will come to an end may not have a simple answer. It may be that the universe is not so much a story with a beginning and an end, but a vast, ever-evolving process that continues to unfold in ways we cannot fully comprehend. What we do know is that the universe and time, in their infinite complexity, are deeply intertwined with the very fabric of our existence. As we continue to explore the cosmos, we may one day uncover new answers, new truths that will help us understand our place in the grand scheme of things. But until then, as we drift further into the mystery of the universe, we are left with one final thought. The end of time may not be the end of everything. It may simply be the end of what we know, the end of the story as we understand it. And as the universe continues to evolve, as it stretches and expands, we are left to wonder, what comes after the end of time? Will there be something beyond the final moment, a new beginning? Or will the universe fade into nothingness, leaving behind only the memory of motion, the echo of all that once was? And so, as we stand at the edge of this cosmic journey, we are reminded that time, like the universe itself, is a force that we can only begin to understand. It is both a measure of our existence and a reminder of its impermanence. Each moment we live is a fleeting echo in the grand symphony of the cosmos, and in that fleeting moment we find meaning, purpose, and beauty. As we approach the end of this chapter, we find ourselves facing the same questions that have driven humanity's search for understanding since the dawn of time. What is the nature of the universe? What is the purpose of life? And in the face of the unknown, what does it mean to be human? Perhaps as we continue on this journey, we will find that the answers are not as important as the questions themselves. After all, the universe is not a puzzle to be solved, but a mystery to be embraced. Continuing from where we left off, the questions we face about the end of time, the fate of the universe, and our place within it are far from simple. We have already explored how time itself may ultimately reach its limit, with theories like the heat death, the Big Crunch, or the Big Rip offering different possibilities for the universe's eventual fate. But even as we venture deeper into these possibilities, one thing becomes clear. The more we understand the universe, the more we realize how much we still do not know. As we contemplate the end of time, we must ask ourselves, is it possible that our understanding of time itself is incomplete? After all, we see time as linear, with a distinct past, present, and future. But in the realm of theoretical physics, this notion begins to crumble. According to the famous physicist Albert Einstein, time is not an absolute concept, it is relative, depending on the observer's position and motion within the fabric of space-time. In Einstein's theory of relativity, time bends and stretches depending on how fast an object is moving or how deep it is in a gravitational field. This principle is not just an abstract idea, it has been proven through experiments, such as the observation of time dilation around black holes, or the adjustments made to the GPS system which compensates for the effects of time dilation caused by the Earth's gravity. This leads us to ask, if time can bend, twist, and warp, what happens when the very fabric of space-time itself begins to unravel? In our search for answers, we encounter the concept of singularities, regions where gravity becomes so intense that it warps space and time beyond recognition. The most famous example is the black hole. Black holes are the result of massive stars collapsing under their own gravity, creating a point of infinite density known as a singularity. In these regions, time and space as we know them cease to operate in the familiar ways we experience them on Earth. The fabric of reality itself is stretched, creating a place where the very laws of physics appear to break down. Inside a black hole, nothing can escape, not even light. This is why they are called black holes. And within their event horizon, where the pull of gravity becomes so strong that even light cannot escape, time seems to stand still. To an observer outside the black hole, time slows down near the event horizon. But for something falling into the black hole, it experiences time normally until it reaches the singularity, where the concept of time itself becomes meaningless. This dramatic distortion of time raises the possibility that black holes might be gateways to other dimensions, where time operates in fundamentally different ways. Could these cosmic anomalies hold the key to understanding what happens when time itself collapses? This leads us to another fascinating concept, the potential for time to be cyclical. Some theories propose that instead of a linear progression, the universe may go through cycles of expansion and contraction, known as the Big Bounce. This theory suggests that after the universe reaches its maximum expansion, it will begin to contract, eventually collapsing into another Big Bang, where the process begins anew. Instead, it would loop, stretching and contracting in an eternal dance, with each cycle of expansion and contraction leading to a new universe. If the universe is indeed cyclical, it would mean that the end of one epoch would not be the end of time, but merely a transition to the next stage of cosmic evolution. However, despite these theories, we still lack a complete understanding of time's true nature. Time, as we experience it, is a human construct, a way for us to measure the movement of events and the passing of moments. But in the vastness of the universe, time might not behave in the same way we expect. What if time is not a constant, but a malleable, evolving force that operates differently depending on where and how we observe it? Moreover, even as we ponder the eventual end of time, we must remember that time itself is intertwined with life. The concept of time is inseparable from the rhythms of nature, the cycles of birth, growth, decay, and death. Life, as we know it, is governed by the passage of time. Our biological clocks, the changing of the seasons, and the cycles of the moon and the sun all shape our lives and our perceptions of time. But what happens when life itself begins to fade? If the universe reaches its end, will life as we know it be extinguished too? Or will life find a way to adapt to the changing nature of time and space? As we move closer to the final chapters of this cosmic journey, the mystery of time becomes even more profound. Time is not just a measure of the passing of moments. It is the thread that binds the universe together. It is the heartbeat of existence itself, marking every change, every moment of motion, and every transformation. The end of time, then, is not just the end of the universe, it's the end of everything we understand about existence. But as we delve deeper into these mysteries, we begin to realize something extraordinary. Even in the face of the unknown, there is beauty. The very fact that time exists, that we are part of this incredible cosmic story, is a gift. The universe, with all its spinning galaxies, its stars, and its mysteries, is not just a machine of physics, it is a work of art, a dance of motion and time, unfolding across the vastness of space. And we, as conscious beings, are able to witness it. So, as we continue our journey through the cosmos, we are reminded of the incredible mystery of time and motion. Whether it ends in a quiet, slow fade into nothingness, or whether it will one day restart with a new cosmic cycle, we are left with a profound sense of awe at the beauty of the universe and our place within it. Perhaps in the end, the most important question is not what happens when time ends, but how we choose to live in the time we have. Because, as we have learned, time may be fleeting, but it is also precious. Every moment we experience is a part of the grand story of the universe, a story that is still unfolding. So as we stand on the precipice of this cosmic journey, we are reminded that the universe itself is a reflection of motion, a dance of time and energy that transcends our understanding. The end of time may be inevitable, but for now, we are part of the motion. We are the universe experiencing itself in the brief moment we call now. Take a moment to reflect. You are part of the cosmic dance, a brief yet beautiful echo in the grand story of the universe. And even as time continues its journey, we are left with one final thought. How will you live in this moment? How will you embrace the motion, the beauty, and the mystery of existence? As we venture further into the unknown, there is one question that remains at the core of our exploration. What is the true nature of the universe? What forces are at play, guiding the motion of everything we see and experience? We have witnessed how time itself bends, warps, and stretches, shaping the very fabric of existence. But even more pressing is the question of what holds the universe together, what gives it structure and form, and what keeps it from unraveling into chaos. At the heart of this question lies the mysterious force known as gravity. For centuries, gravity was one of the greatest puzzles in science. It is the force that governs the motion of planets, stars, galaxies, and even light itself. Yet, despite its importance, gravity remained an enigma. It was a force that acted across vast distances, binding galaxies together, shaping the structure of the cosmos, and yet it seemed to have no origin, no mechanism by which it acted. It wasn't until the early 20th century, with the advent of Einstein's theory of general relativity, that we began to unravel the true nature of gravity. According to Einstein, gravity is not a force in the traditional sense, but rather the result of the curvature of space-time caused by massive objects. In this view, mass and energy warp the fabric of space-time, causing it to curve, and this curvature is what we perceive as gravity. It's a profound shift in our understanding of the universe, a realization that the very geometry of space-time is shaped by the presence of mass and energy. But as we look deeper, we begin to realize that gravity is not the only force at work in the universe. In fact, gravity is just one of the four fundamental forces that govern the behavior of everything in the cosmos. The other three forces, electromagnetic force, the strong nuclear force, and the weak nuclear force, are just as important, though their effects are often less apparent on the grand scale of galaxies and stars. The electromagnetic force, for example, is the force that governs the behavior of charged particles. It is responsible for everything from the interactions between atoms to the behavior of light itself. The strong nuclear force holds atomic nuclei together, keeping protons and neutrons bound in the heart of every atom. And the weak nuclear force is responsible for certain types of radioactive decay, playing a crucial role in the processes that power stars. Together, these four forces create the structure of the universe, shaping everything from the formation of galaxies to the interactions between subatomic particles. But despite their fundamental importance, we still do not fully understand how these forces work together. In particular, scientists have long struggled to unify gravity with the other three forces, leading to the search for a theory of everything, a single framework that can explain how all the forces of the universe are interconnected. One of the most promising candidates for this theory is string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. According to string theory, these strings can vibrate at different frequencies, and their vibrations give rise to the various forces and particles that we observe in the universe. String theory offers the possibility of a unified theory that could explain the behavior of all the fundamental forces, but it is still a work in progress, with many questions remaining unanswered. As we look at the grand scale of the universe, it becomes clear that these forces, gravity, electromagnetism, the strong and weak nuclear forces, are not just abstract concepts, but the very building blocks of reality itself. They shape the stars, the planets, the galaxies, and even the fabric of space-time itself. And yet, we still don't fully understand how they work together. It is as if the universe is a vast, intricate puzzle, with each force playing a unique role in its design. But there is more to this mystery than just the forces of nature. There is a deeper question that we must ask. What is the true nature of the universe's motion? We've seen how rotation defines the flow of time, how the universe itself spins in ways that we cannot always perceive. But is there more to this motion than we realize? Could there be deeper, more fundamental forces at play? Forces that transcend the limits of our current understanding? As we look out into the cosmos, we are reminded of the vastness of the universe, an expanse so large that our minds can hardly comprehend it. Yet, despite its size, the universe is not a static, unchanging place. It is a dynamic, living entity, full of motion and energy. From the rotation of galaxies to the expansion of the universe itself, the cosmos is constantly in motion, constantly shifting and evolving. This motion is not random. It is guided by the fundamental forces that govern the universe, forces that shape everything from the smallest particles to the largest galaxies. But even as we understand more about these forces, we are left with one lingering question. What lies beyond them? What forces are at work in the universe that we have not yet discovered? Perhaps the answer lies in the very structure of space-time itself. As we have seen, space-time is not a passive backdrop against which events unfold, but an active participant in the motion of the universe. It curves, twists, and bends in response to the forces that shape it, creating a dynamic, ever-changing landscape. In this view, the universe is not just a collection of objects moving through space. It is a living, breathing entity with a structure that is constantly evolving. And if space-time is alive, then perhaps there is more to the universe's motion than we realize. Could there be deeper forces at work? Forces that transcend the known laws of physics and shape the very fabric of reality? Could the universe itself be evolving in ways that we cannot yet perceive, moving towards some greater understanding of its own existence? As we continue our journey through the cosmos, we are reminded of the beauty and mystery that surrounds us. The universe is a vast, intricate web of forces and motion, a dance of energy and time that is constantly unfolding. And as we strive to understand its true nature, we are left with one final thought. The universe is not a machine, but a living, breathing entity, full of motion and mystery, waiting to be explored. Take a moment to reflect. You are a part of this vast cosmic journey, a small but significant piece of the grand puzzle that makes up the universe. And as we move forward, we continue to seek answers to the greatest questions of all. What is the true nature of the universe? What forces shape it? And what lies beyond the boundaries of our understanding? So, as we stand at the threshold of this grand exploration, we are left with one final question. What will we discover next? What mysteries will we uncover as we continue our journey into the heart of the universe? Only time will tell, but one thing is certain, the journey is far from over. And with that, we move forward, continuing our quest for knowledge and embracing the infinite mysteries that lie ahead. As we push deeper into the heart of these cosmic questions, we encounter a profound paradox that stretches our understanding of time, space, and existence itself. the role of dark energy. In a universe that seems so rich in observable forces, gravity, electromagnetism, the nuclear forces, what is this mysterious force that is driving the universe apart? Why is the universe expanding, and what will become of that expanding? We have long known that the universe is not static. Ever since the discovery made by Edwin Hubble in the 1920s, we've known that galaxies are receding from each other, stretching the fabric of space-time itself. This observation confirmed the Big Bang theory and suggested that the universe had a beginning, a moment when all the matter and energy in the cosmos were compressed into an infinitesimally small point, a singularity. From that moment, the universe began to expand, a process that has continued ever since. But while that expansion was initially thought to be slowing due to gravitational attraction, a startling discovery was made at the end of the 20th century. In the late 1990s, two teams of astronomers studying Type Ia supernovae, the brilliant explosions of dying stars, found that these supernovae were farther away than expected.
The universe's expansion was not slowing down.
In fact, it was accelerating. This discovery was one of the most significant in cosmology because it implied the presence of an unknown force, one that seemed to be counteracting gravity and driving galaxies apart. That force was named dark energy, a mysterious, repulsive force that makes up approximately 68% of the universe's total energy density. But what is dark energy? How does it work? We know it exists because we see its effects on the large scale, but it does not interact with matter in any detectable way. It doesn't emit light, nor does it absorb or reflect radiation. It remains invisible to our most advanced instruments. Scientists have speculated that dark energy may be a property of space itself, a vacuum energy that permeates all of existence, exerting a repulsive force on galaxies and other large structures. One of the leading theories of dark energy comes from Einstein's general theory of relativity, where he proposed the idea of the cosmological constant, a term he added to his equations to account for a static universe. This term was later discarded when it became clear that the universe was expanding, but now it seems that Einstein's cosmological constant may have been more prophetic than anyone could have imagined. This constant could represent a form of energy inherent to space itself, an energy that causes the fabric of space-time to stretch and expand. Another possibility is that dark energy is linked to quantum mechanics. At the quantum level, empty space is far from empty. It is filled with quantum fluctuations, tiny, temporary changes in energy that spontaneously appear and disappear. These fluctuations might be responsible for the repulsive force that is observed on cosmic scales. Some scientists believe that dark energy could be a manifestation of this quantum behavior, a fundamental force that is a consequence of the very nature of space-time itself. But even with these theories, dark energy remains one of the greatest mysteries in cosmology. The more we study it, the less we seem to understand. We know that dark energy is responsible for the accelerated expansion of the universe, but why it exists or how it fits into the larger framework of physics is still uncertain. Some scientists even suggest that dark energy might not be a force at all, but could represent a flaw in our understanding of gravity. Perhaps there is something we've missed, something fundamental to the structure of the universe that we haven't yet discovered. The implications of dark energy are far-reaching. If dark energy continues to drive the universe's expansion, it could eventually lead to what is called the Big Freeze. In this scenario, the universe would continue to expand at an ever-increasing rate, causing galaxies, stars, and eventually even atoms themselves to become too far apart to interact. As galaxies move further from one another, the night sky would grow darker, and the universe would grow colder until all that remains is a vast, empty, and silent space. Alternatively, there are theories that dark energy could eventually lose its dominance, perhaps after billions of years, allowing gravity to take over once again. This could lead to the Big Crunch, a scenario in which the universe collapses back in on itself, contracting into a singularity once more. In this scenario, the cycle of expansion and contraction could continue indefinitely, each cycle giving birth to a new universe. However, these theories remain speculative. While dark energy plays a critical role in our understanding of the universe's fate, its true nature remains elusive. It's a cosmic riddle that invites us to challenge our most basic assumptions about space, time, and the forces that shape them. Could dark energy be the key to unlocking the next chapter in the story of the universe? Or could it be a sign that we are on the brink of discovering something even more profound? Something that defies our understanding of physics? As we continue our journey through the cosmos, we must grapple with these questions, pushing the boundaries of what we know and searching for answers that lie beyond the stars.
The universe is a vast and mysterious place filled with wonders and unknowns.
And yet, every discovery we make brings us one step closer to understanding the forces that drive it. As we look out into the infinite expanse, we are reminded of the grand scale of our existence, one that stretches from the smallest particles to the farthest galaxies, all moving together, bound by the same forces, spinning in a cosmic dance that has lasted for eons. But even as we explore the mysteries of dark energy and the fate of the universe, we must ask ourselves, what is our place in all of this? How do we fit into this grand cosmic scheme? Are we simply passengers, carried along by the motion of the universe? Or is there something more to our existence? Something deeper, more meaningful, that transcends the forces of nature? In the next part of our journey, we will explore this very question, delving into the role of life in the universe and whether our consciousness has any connection to the cosmic forces that shape everything we know. Stay with me as we continue this exploration and prepare for revelations that will stretch the boundaries of our understanding even further. As we come to the end of our journey, we find ourselves looking out at the vast, infinite expanse of the cosmos, a tapestry of stars and galaxies, a universe in motion, constantly evolving, yet always connected by a common thread. We've explored the mysterious forces that shape the universe: gravity, dark energy, the cosmic spin that defines the rhythm of time itself. We've learned how rotation is not just a property of matter, but a force that has shaped the universe since its very beginning. It is the pulse of existence, the invisible dance that carries everything forward, from the smallest particles to the grandest galaxies. But perhaps the most profound realization of all is this: we too are part of this motion. Every atom in our bodies, every heartbeat, every thought is a continuation of that ancient cosmic rotation. We are not separate from the universe, we are a part of it. We carry its history in our very cells, a living testament to the cosmic forces that have shaped us. And as we move through time, we are in a sense the universe remembering itself. It's humbling to think that the same forces that govern the motion of galaxies and stars also govern the smallest moments of our lives. The rhythm of day and night, the turning of the seasons, the very beat of our hearts, all are echoes of the same cosmic dance. We are not just passengers in this journey. We are active participants, part of a grand, beautiful pattern that stretches from the beginning of time to the infinite future. As we stand here, gazing into the cosmos, we are reminded of how little we truly know about the universe, and yet how deeply connected we are to it. Our lives, our stories, are written in the stars. The motion that began with the Big Bang continues to ripple through the universe, shaping the course of everything, from the birth of stars to the emergence of life. And as we look out into the night sky, we are reminded that we too are part of this ever-turning wheel of existence. In this vast, infinite universe, we are but a tiny speck. Yet we are also the universe in all its complexity, its beauty, and its mystery. As we continue to explore, to learn, and to grow, we are not just uncovering the secrets of the cosmos, for in the end, the universe is not just a place we exist in, it is a part of who we are. So as we drift through the quiet, endless night, let us remember, we are not still. We are spinning, always in motion, always part of this grand cosmic dance. And as we continue to explore the mysteries of the universe, we are, in a way, learning more about the very essence of our existence. Thank you for joining me on this journey, for sharing in the wonder of the cosmos. As we close this chapter, remember that the universe is always in motion, and so are we. And in that motion, we find our place, our purpose, and our connection to everything that has ever been and everything that ever will be. May your journey through life be as peaceful as the turning of the stars, as steady as the rotation of the earth, and as boundless as the universe itself. Until we meet again beneath the endless sky, keep spinning, keep dreaming, and keep reaching for the stars.